Hello everyone, welcome to MIPI Debug for I3C Primer, a joint presentation by NXP, Silvaco and Intel. I am Rajiv Hurlikopi, an application engineer at Silvaco supporting the I3C family of products. Today I'm joined by Paul Kimmelman of NXP and Rolf Kunis of Intel. First it will be Paul who will be providing us basic building block information about MIPI's debug for I3C.
We will start out by explaining why I3C debug was conceived by MIPI and how it fits into the broader MIPI debug mechanisms and its value over the use of traditional debug schemes such as JTAG, single wire debug, etc. This slide shows traditional debug environment by using I3C. As you can see in the upper drawing, there's a dongle connected onto an I3C bus, which is used both for application use as well as in this case for debug when it's connected. In the lower one, the same thing, but using sideband signals from a USB Type-C. We'll explain that more in a later slide. This slide shows a more interesting environment where in fact, the debug is through an application processor already on the board. It's only showing a couple targets, but there could be, of course, many more. The point being that the application processor is part of the debug process rather than the use of a dongle, and the connection in this case would be USB, or could be Ethernet or other ways to communicate between the host and the apps processor. This slide shows some of the goals of debug over I3C, and in particular taking advantage of I3C's existing capabilities, minimum number of pins, the use of multi-drop, the host role controller swapping so that a debug controller can join, as well as main app processor. Of course, the ability for devices to be able to disconnect and reconnect to a bus without causing damage. And of course, the ability to be able to mix both application and debug on the same bus using existing I3C mechanisms. So now we'll move on from why we want to do this and what the goals were to how it's actually implemented in an I3C system. This slide shows how I3C debug is built on top of the existing MIPI debug mechanism with a replacement of transport and some additional capabilities. On the left, you can see that we have a controller, which is for debugging. We have target systems, which we can then debug. And as we can see on the right-hand side, the mechanism is intended to be flexible. This is, of course, a larger system than you might have in a very small I3C device, but it's a whole scalable system that allows for very simple down to state machine and MCUs all the way up to apps processors, and we'll see a bit more of that on the next slide. This slide shows the modularity of the debug system over I3C and in fact the MIPI debug system. Now this drawing is showing a lot more than what you would have in a normal system, a normal target, but it shows the range of capabilities. So for example, sneak peek and SAM would not coexist normally on a device. You'd use one or the other. If you're using SAM, you may not have trace. You may have integrated trace within the SAM device, but it does show the different capabilities. And of course, these are specific to the debug. The application uses of the same I3C controller are not shown, but would be there as well, allowing the maximum modularity and reuse. This slide is showing a SAM connection, which we saw on the previous slide. The SAM would be used for lower-end devices, state machine devices, MCUs, etc. It's a simplified interface as opposed to something like sneak peek, which would be used on an apps processor. As you can see in this drawing, the application is also using the I3C bus, and then the SAM is mapped, in this case, to an ARM DAP, but it could be to any other processor, proprietary, RISC-V, etc. The point of this is that the software on the controller and in the debugger map to the necessary debug capabilities of the system, the target system that you're accessing, and so the scalability is built in. SAM or sneak peek is simply providing the framework from which those messages can be created. This slide is showing the USB Type-C connection that we discussed in the earlier slide. As you can see, the normal USB connection is used to the apps processor or MCU on the system, on the board, and then the sideband signals, which are not used by the USB, are used then for debug. So as long as a dongle can be connected through it or a host system provides access to it, then we have access to debugging onto an I3C bus, which otherwise is only used for application. So similar to the normal dongle connection, this just simply takes advantage of an existing connector and provides additional capabilities without having to have special board attachment. On this slide, we're showing, unlike the Type C sidebands, this is a case where through the USB.org, a new type of device class has been being added, which is the I3C device class. Its intent is to be able to use USB to communicate with an apps processor or an MCU or a dedicated tiny device that can be used to access the I3C bus. Now, this could be used, of course, for other purposes besides debug, but one of its values is the ability to use it for debug, whether that's of the type we showed where the apps processor itself is debugging other devices on the I3C bus, or whether it's an external connection that allows debug of I3C components, including the apps processor or main processor through I3C, and then using a standardized host interface from the hosted system side as shown here on the left. In our demonstration, we'll be showing a very simple debug system that would represent a core piece of what you would use in a normal system. So we have a hosted system that's running a debugger. In this case, we're communicating over USB to an I3C controller running on an FPGA. So this would be like an MCU-based controller, or other, could be an apps processor. It's communicating over the I3C bus, in this case to a target system. We're only going to show one, but of course it could be as many as you like. That target system is running a RISC-V processor, and we have I3C target IP that's also target plus debug. So we have application things going on, but we also have debug system. And this allows access to the memory system and to the processor. Obviously, this does not have to be a RISC-V system. This could be an ARM, could be a DSP, could be a proprietary system, whatever. It doesn't really matter. The point, in fact, that is the point. The host system could adapt to multiple devices on this bus, each one with a very different type of system underneath it, and it just simply adapts the debug to the necessary one, but using the exact same I3C componentry and the exact same I3C communication mechanism, including the ability to have interrupts from this system that tell you, for example, if this hit a breakpoint and stopped.
Thank you, Paul. And for the rest of our allocated time, I'll be talking about the details of a system we built to demonstrate the basic working of debug for I3C. Please note that we are not using any sideband USB signals in our demo. We are directly connecting the I3C bus on the dongle to the application processor, which is also used for debug. The demo consists of two boards. First, the DE10 Lite board from Terasic. It is connected to the PC through USB. It has an ARM Cortex-M0 subsystem with an I3C controller that is managing the I3C bus. The Cortex-M0 runs a command line interface on the host PC that is connected to it. It can send I3C CCCs, including the debug-related CCCs, on the I3C bus via the I3C controller that is connected to it. The second board in our demo is the ZCU104 board from Xilinx. It contains the RISC-V subsystem with I3C target and debug interface module called the Simplified Address Mapped or SAM debug add-on. It is designed to allow for debug, trace, and test/failure analysis. The connection from the DE10 Lite board running the DTS system to the ZCU104 board with RISC-V subsystem that is being debugged is the two-wire I3C bus as shown here, and of course the ground wire that connects the two boards. From the command line, we can send debug CCCs such as read a code register or get the status of an interrupt on the I3C bus. The I3C target on RISC-V subsystem responds with an appropriate response back on the I3C bus. With that, we complete the debug for I3C demo. I would like to thank Paul Kimmelman of NXP and Rolf Kunis of Intel for their valuable contribution to today's demo and presentation. For additional details or questions, please email us at ipsupport@silvaco.com. Thank you very much.